third day of our derivative unit. We want to find the equation of the secant lines here, TA, TB, and TC. In order to find the equation of two lines, you need two things. You need a point, and you need a slope. So let's look real quick at these 3 points. Let's make them a little easier to use. Let's go ahead and mark A as the point 6, comma 8. That is A. Let's mark B as the point 5, comma 4.5, which I'm going to write as 9 halves. And the point C, which is 4, comma 2. And finally the point T, which has the coordinates 3, comma 1 half. So notice we've got some useful formulas on the side here. Y equals mx plus b, that is our slope-intercept form, m being the slope there, and b being the y-intercept. We have y minus y1 equals m times x minus x1. That is point-slope form. Again, we have slope m, and this time we've substituted in some point x1, comma y1. This will become your favorite form of the linear equation. I promise you that. It is so useful. And then finally, remember that we have m representing our slope, which is the change in y over the change in x, aka rise over run. And you can find the change in y by subtracting your two y values and dividing by the change in x, which is the difference in your two x values. So let's go ahead and find some slopes first. Let's find the slope of line TA. So let's choose point A as our second point and point T as our first point, and let's do 8 minus 1 half, 8 minus 1 half over 6 minus 3, and so we're going to get 7.5 over 3, which would be a terrible way to write your answer. So I am going to simplify this first by multiplying by 2 to get 15 over, multiplying by 2 in the denominator as well, 15 over 6 equals, now I can divide both of those by 3. 15 divided by 3 is 5 over 6 divided by 3 is 2. So that slope is 5 halves. And now all I have to do to write my equation is substitute in a point, so I could choose point A, and that slope in 2-point slope form. So I could get y minus the y value of that point, which is 8. Y minus 8 equals our slope, which is 5 halves, times x minus the x value of that same point, which is 6. And you are done. That is your equation. You don't have to take it any farther. However, if we ourselves do want to take it farther, then we need to write this in slope-intercept form. So I'm going to get y equals 5 halves x. By distributing in that 5 halves to the x, I'm going to distribute in the 5 halves to the 6 as well. So I'm going to get minus 30 over 2 plus 8, bringing that 8 over. Well, 30 over 2 is 15, so I have minus 15 plus 8. So I get y equals 5 halves x minus 7. So it's good to definitely know how to get between forms. But if you are able to use point-slope form, then you should use point-slope form because it's so easy. So that's the equation of the line, and that is TA. I am not going to go through and do TB and TC. You should do that yourself and check to make sure you are correct. But that's the basic idea of finding the equation of a line between 2 points. So now let's look at this weird diagram. Notice at the top we have the limit as delta x goes to 0 of delta y over delta x, aka the slope, change in y over change in x. And this is just a fancy way, this is our limit definition of a derivative, is our fancy way of writing the slope. Because if you think about this diagram right here, we have our x2 and x1, and we have, oh, I'm sorry, that was weird. We have our x2 and we have our y2 are the coordinates of that point, and then we have our x1 and y1 are the coordinates of that point. And notice this limit is going to take the second y value, which is f of c plus delta x, and subtract from it the first y value to get our change in y, and it's going to divide it by delta x, which is the difference in those two values, x2 minus x1. And so since this is a limit, it is exactly like what we have on that warm-up. We have secant lines where this point is staying the same, but this point A is moving closer and closer and closer down that line. And it's getting closer and closer to that point, T, right there. And as we get closer and closer, the slope of this tangent, the slope of these secant lines here gets closer and closer to the slope of that tangent line. That's what this diagram is showing right here. As you move that black point to the right, as delta x gets smaller and smaller and smaller, the secant lines get closer and closer to approaching that tangent line. And that is what this limit represents. So this idea of a tangent line was one of the original calculus problems. Remember, it all kind of started with geometry, where you have a circle with a center, and you can draw the radius out to some point, and the tangent line to that point on the circle will form a right angle with that radius. That was kind of the original idea, and then they expanded it to functions in general, where you have some curve, and we want to find the point that is tangent to that curve at some x value. And so, in order to answer that question, you need to use calculus. So that's what we're going to do now. But before we can, let's make sure we remember how to do the power rule, because it's all going to come down to taking derivatives, which represent the value of the slope of the tangent line. So let's use the power rule to take some derivatives. If I take the derivative of f prime of x, power rule says to multiply the exponent by the coefficient. So 2 times 3 is 6 times x, and we are dropping the power by 1, so it's just going to stay an x. Second one, same idea. Let's pretend like that says minus 2/3 x squared right there. So if I take g prime of x, I'm going to multiply the 3 by the 4, the exponent by the coefficient to get 12x. I'm going to subtract 1 from my power to take it from x cubed to x squared. Minus, I'm going to use the power rule again, multiply my power of 2 by my coefficient of 2/3 to get minus 4/3 x. Subtract 1 from the power, and it stays an x. And then that constant term right there goes to 0, so I get my derivative function. Go ahead and try the rest of these, see what you can get, and then check your answers with me. So let's go ahead and do h of x here. Power rule running through. 3 times 2/3 gives me 2x. Drop the power by 1, I get squared. Plus 2 times 7 gives me 14 over 10, which is the same as 7 over 5. X squared minus the derivative of 2x is 2. And the constant term goes away. So that is my derivative, h prime of x. I of x here, again, first thing you need to do is rewrite negative 3 times x to the power of 1/2. now we can use the power rule. Wow, that's 1/2 right there. Now we can use the power rule to get -3 times 1/2 is -3/2 times x to the -1/2 because we are subtracting 1. So I'm going to write that as -3 over, whoa, no I'm not. I'm going to write that as, wait, whoa, yes I am. I'm going to write that as -3 over 2 times the square root of x because the negative exponent, again, brings it down. So that is I prime of x. Go to j of x. We are going to rewrite this as 4 times the cube root of x squared is the same as x to the 2/3. Remember, the numerator is the power, and the denominator is the base. So now I can use the power rule to get j prime of x equals 2/3 times 4 is going to give me 8/3 times x to the -1/3 when you subtract 1 from 2/3. And I'm going to simplify that as 8 over 3x to the 1/3. Or if you want to write it as 8 over 3 times the cube root of x, you can definitely do that as well. K of x is already written in a form we can use the power rule with, so we're going to get k prime of x equals 5 over 4 times x to the 1/4, which you could write as 5 times the 4th root of x over 4. Okay, getting through them, rewrite this as 3 times x to the -2nd, and then we've got -6 times x to the -3rd, which is -6 over x cubed for our L prime of x function there. M of x, same thing, rewrite it 10x to the -3rd to get m prime of x equals -30 x to the -4th, which is, of course, -30 over x to the 4th. And one last problem here. 1 over x plus 2 over x squared we'll write as x to the -1st plus 2x to the -2nd, so that when we take the power rule, we get n prime of x equals -x to the -2nd minus 4x to the -3rd, which we will rewrite as -1 over x squared minus 4 over x cubed. And those are all of our derivatives right there. Bunch of good practice problems. So now let's think about what we said a moment ago. To write the equation of a line, a linear equation, you need to know a point, and you need to know a slope. I just yawned. Did that make you yawn? So, again, recognize that the derivative function is representing the instantaneous slope, aka the slope of the tangent line, for every single x value. So, if we have a function f of x, and we use the power rule to take the derivative of f of x to get 6x in this case, we can then use whatever x value we want to know the slope of the tangent line at. Say we want to know the slope of the tangent line when x is 2. We can plug that into our derivative function, f prime of 2 equals 6 times 2 equals 12. So this is saying, if you think about the function 3x squared plus 2, which is going to look like that, if you go to the x value of 2, and you graph the tangent line to the equation at that point, that tangent line will have a slope of 12. Huge idea here. So we have a limit problem here. Again, our technique for this limit problem is to multiply by the, find a common denominator by multiplying by the denominator of the other fraction over itself. So I'm going to get 3 times 1, rewrite this limit real quick as x goes to 3. 3 times 1 is 3 minus 1 times x is x over 3 times x is 3x all over x minus 3, which I'm going to rewrite as the limit as x approaches 3 of 3 minus x over 3x times 1 over x minus 3 multiplied by the reciprocal there. Well, look, 3 minus x over x minus 3 right there, they're almost the same thing, except one is the opposite of the other. So I'm going to rewrite this as the limit as x approaches 3 as negative x minus 3 times, 1, and then we have our over 3x over x minus 3, and now you can see that boom, boom, that eliminates, and you're left with negative 1 over 3x. No, just kidding, you're left with the limit as x goes to 3 of negative 1 over 3x, which is negative 1 over 3 times 3, which is negative 1/9. And now I want you to do this problem, which is 1 over x times, blah, 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 blah. Nope, I can't talk. What I want you to do is I want you to find the derivative at the x value of 3. So use the power rule. First, rewrite this as x to the negative first. Now let's use the power rule to write f prime of x is negative x to the negative 2, which is negative 1 over x squared. And we're looking at the x value of 3, so plug it into the function. F prime of 3 is going to equal negative 1 over 3 squared, so we get negative 1/9, which was the answer to our last problem. Alrighty. Now let's do this problem as well. Limit as delta x goes to 0. Again, this time we're going to use the technique of multiplying by the conjugate. So I'm going to multiply by delta x plus 16 plus 4 over the square root of delta x plus 16 plus 4. And we like conjugates because when you multiply them together, you get the first term squared, so I end up with delta x plus 16 without the square root, minus the second term squared, which is 4 squared is 16, and that's all over delta x times the square root of delta x plus 16 plus 4. As such, of course, this is all still the limit as delta x goes to 0. So now I can simplify 16 and negative 16, delta x and a delta x, so I get the limit of 1, limit as x, delta x goes to 0, of 1 over the square root of delta x plus 16 plus 4, which is 1 over the square root of 16 plus 4, which is 1 over 8. Maybe you can predict what the answer to this is going to be, but again, I want to find the slope of the tangent line at the given point for the given function, so I need to find h prime of x, so I need to rewrite this as x to the 1/2 to get my derivative function, which will be 1 over 2 root x using the power rule. X value is 16, so plug it in there to get h prime of 16 equals 1 over 2 times the square root of 16 equals 1 over 2 times 4 equals 1/8. Weird, same answer again. So stare at these now and see if you notice anything. So what I want you to notice is this. Notice in the limit problem, the first term was 1 over x. And when we took the derivative, we were taking the derivative of the function 1 over x. Notice that the limit was as x was approaching 3, right there, and we were taking the derivative at the x value of 3. And when we did those two things, we ended up with the same answer. Same exact thing when it was written in the delta x form. Except it looks a little bit different. This time our function was the square root of x, and we had the square root of this weird thing, and we also know that we were looking for the derivative when the x value was 16, and 16 was all up in that weird thing, and again we got the same answer. So what is going on here? Take a look at the green and the red and think about if you see what's happening. You were looking at the limit definition of a derivative at a specific point. So the first one was written as the limit as x approaches 3 of 1 over x minus 1 over 3 all over x minus 3. So look at the pieces. Our first term was our function, so f of x equals 1 over x. The limit that our function was going to, the x value that we were interested in, aka our c value, and here they're calling it a, but we're going to call it c. It doesn't matter. It doesn't matter. I promise you, it doesn't matter. Change all of those to c's, or leave them as a's. It doesn't matter. But the c value that we were looking at was 3. Now notice the second term in the numerator up there was just your function with that c value plugged in. So that was f of 3 right there. And if you want to talk about the other function we looked at, that was the limit. It said delta x, but really that's the same as these h limits. Limit as h goes to 0 of the square root of h plus 16 minus, it was saying 4 over h, and the same situation here. This time it's not our first term as the function, but it's our first term with that c value plugged into it plus an h. Well, there's our first term with the c value plus an h. So that's telling me then that the c value in question, that c value there, is that 16. So f of x is the square root of x, and the c value that I'm looking at is 16. And then again, recognize that the minus 4, that is f of our c value, aka the square root of 16 is 4. Now the limit, the answer to this, is going to be the derivative at that point. So this would be f prime of 3, and this one would be f prime of 16. So soak that in. So from now on, when we see these limit problems, we can identify the function, which in this case is going to be f of x equals 1 over x cubed, which I'm going to write again as x to the negative third. We can take the derivative of that function, f prime of x, using the power rule, so we can get negative 3 over x to the fourth. And then we can plug in our c value to that function, the derivative, and get f prime of 2 equals negative 3 over 2 to the fourth equals negative 3 over 16. We can recognize that that is asking for the derivative at the x value of 2, and we can just jump to that answer instead of going through the limit process. So again, you should identify your function. I would then find the derivative, f prime of x, figure out what value we're trying to find the derivative at, and then plug it in to the derivative function. So let's look at this one. F of x, again, is your first term there. So f of x has to equal 3 times x to the negative fourth. If we take the derivative, f prime of x, we will get negative 12 over x to the fifth. If we then plug in the c value, we will get our derivative at that point, at the x value of 2, negative 12 over x to the fifth gives me negative 12 over 32, which gives me negative 6 over 16, which gives me negative 3 over 8. Simplify. Lots of times the derivatives will look like this as well, which is a little harder to recognize the function, but again, it's in the form limit as h goes to 0 of f of c plus h, c being the point we're looking at, minus f of c all over h. So maybe that helps you identify that the function is 2x cubed, 2x cubed. That is f of x. So we can take the derivative f prime of x and get 6x squared, and we can plug in the x value we are interested in, which is 1, to get the derivative of x at the x value of 2 is 6. Can you hear my dog whining? Whoa, crybaby.